Okay, so we are going through some of the notebook from Qiskit algorithm, and today we're going through a few that I selected for Qiskit machine learning and also Qiskit nature. So this is probably the last class for Qiskit, and then Wednesday I'm going to move on to Q-tip. So again, this is also going to be a really brief survey of these topics. And I don't think I have time to talk about classical neural network, but with vague idea, then it's probably okay. Yeah, so this is from Qiskit machine learning. Let me also go through that. Qiskit machine learning. GitHub. Okay, there is. Maybe tutorial and go directly to that. This is a different interface. Okay. Um, yeah, so this interface looks nicer. Yeah, it's a web based. But if you go to the GitHub, GitHub, really the bare bone notebook. You go to the documentation, go to tutorial, and you can select any of these notebook. Okay. Okay, so I'm going to just focus on specific one I've chosen. This is the 12th one on this list. Oh no, this is different. It's not 12. 12 is just I named that at 12. So the number naming is should be 02. This the second one here. Okay, maybe I'm covering these three. Okay. Okay, so yeah, so again, this is a package that's maintained by the community. So this is called Qiskit ecosystem. And it has a lot of built-in functions. So for example, neural network classifier and neural network regressor classes that they already designed. So you don't need to worry about the detail, just need to have a bird's eye view and what you want to do, and then you can code it. But here we are learning how to use it. Okay. And what is a quantum neural network? I mean, we don't really have a quantum neural network per se in the sense of classical, but we have quantum circuit and we have variational parameter. So when you hear quantum neural network, just think of it as a quantum circuit. Okay, so both of these classes, they take input a quantum neural network. Okay, the bracket, so it might also be able to take classical neural network. And then, yeah, leveraging it in a specific context. Okay, so in both cases, they also provide a pre-configured variant for convenience. The variation of quantum classifier and variation of quantum regressor. So yeah, so this is the tutorial is about, and it use estimator or sampler method. So estimator would have a estimator QNN, quantum neural network, and sampler quantum neural network, and also variational quantum classifier. So the second part is about regression. First is classification, second part is regression. You can do regression with estimator or a quantum variational regressor. Okay. And right, I think I mentioned you have to install this. This is doesn't come with Qiskit itself. you have to install this. It's very simple. Just use pip install Qiskit-Machine-Learning. If you don't have it, you can install it real time. So that you have all these classes that it can be imported. So yeah, so this is standard Qiskit, standard Qiskit, standard Qiskit. So this real amplitude ZZ feature, I think we have seen very early when we introduced quantum circuit. Okay, now these are from the Qiskit machine learning. They have optimizers, utilities. Okay, optimizer, Cobla, and LBFGSB. These actually appear quite early in very early version of Qiskit, but they somehow enroll this to this machine learning package. For the machine learning package still retain that functions. But there's also on the algorithm that classifier or regressor, you import these classifier. So variational quantum classifier or variational quantum regress. Yeah. And you also import sampler and estimator. And then also circuit, quantity circuit. You need to know where the classes are, to import them. But this give you an example. This global algorithm global really allow you to set some random seeds. So this can be reproduced. Like if you have different time using a different random seed, and you don't know it, you will not get the outcomes that you can check. Okay, so I think I ran this. Okay, I import this. So first is classification. Let me just give you the overall structure. Classification, basically you have, for example, two sets of data or two groups of data, and you want to see which data point is in which group. So, and that's using these classifier. Okay, so this is for classification. The curve you see, we're going into that this is when you optimize the loss function. Okay, so that's a few example, few different way of doing the classifications. Yeah, and then toward the end, there's a regressor that we're going to play with. So you generate like a sine function, but with random deviation from that. And you want to see what is the underlying curve, and you use quantum to do that. There are also other ways, classical, but this I'm going to focus on the quantum because, yeah, quantum programming. Okay, so this here generate random point on the two dimensions from -1 to 1 in each direction. Okay, this is number of samples, 20, so 20 dots, and number input, this means the number of classes. Or this, maybe this, yeah, this means the dimension. Right, this means dimension. Number input meaning the dimension. We have not designed the classes yet. So there is this function. So sum over each list inside the two-dimensional. If the sum is greater than 0, and you can set this to be 1 or 0. So yeah, so I printed out this. This is the x first. This is the x, and the y. Let me also print y. Normally, people just load random data. So let me just print Y. So I printed X and print Y. Okay, Y. I should use Y01. Okay, Y0 is which class? The first point is 1, second point is 1, etc. Last point is 0. Basically, you just take X and Y. If it's greater than 0, then you call it Y, 1. And if not, then it's 0. So basically, it's this line. It add up to 0. It's 1 here and then 0 class here. Okay, so this is really just setting up. Okay. One Y1 hot. Y1 hot. We can print out this. Basically, those with 1 label. Okay. Print. Zero, 1. So this is the vector of which class using the vector to represent a 2-component vector to represent which class. This is vector 0, 1, 2 components 1. This is 1, 0. So this is corresponding to 1, 1, 1, and then 0. Right, and the last one 0. So will be 1, 0. It's like a qubit, right? If we represent qubit, a 2-component 1, 0 will be the 0 state. Okay, so this is really just setting up the data that it shows here. Okay, so then we're doing the classification, and first we use a feature map. Like it's called Z feature map to load the 2-component x0 and 1, which is the coordinate, into the qubits 0 and 1 here. Okay, so these are data where you hold the data, and then you can design what are the variational circuit. So first this is the circuit, neural circuit. Okay, we use real amplitude. Okay, and the classifier we're going to use is really just a classical simulator using state vector. We have seen this, right? Qiskit primitive state vector estimator. So this is our estimator, and then we'll name this estimator underline Q and N is from this class estimator class, estimator Q and N class. Okay. Then you have to tell what is the circuit. This circuit is this QC that we just defined. Estimator is the estimator we call from this class here, state vector. So basically, you just need to define what are the individual drivers, estimator, and then you use this estimator Q and N. Right? You don't need to know the detail. It's really just package. So, and what you do is just say, okay, I take this driver, estimator Q and N, that forward, and then this is the input, and you generate some random weight, right? So there are 8 here. So this is for the input to input this data into this ZZ feature map, and this here it's a random. So using from algorithm globals, random.random, and you just say how many weight we have. I mean, you can print the weight here. So here, the circuit, you could also, you could see QC dot parameter. So this is from X, Y. Here, basically, this is telling us the limited print estimator given in that number of weights. Yeah, so the weight meaning here, because we imagine this is a neural network, so these parameters represent the weight. And the parameter here are just input. I don't know whether you could say there's no, I don't think you can say you see that number of weight. I don't think this will work. There's no, it is there a number of parameters. There's number of parameters, but there's no number of, yeah, basically, yeah, the number way comes when you are using this estimator, when you're calling this. But somehow here it knows it, and when you draw the circuit, it knows that they are a parameter. But I don't know how to access that. Okay. But here it allows us to extract that and then set a random initial weight. Okay, that's here. Basically, if you have time, just change things, print things, and then play with this. No problem. Okay, here is just adding a callback function. This is just to store information to plot the output. So, right, it's stored, and what it does is also clear output. And yeah, and this is just adding the values, the objective function value. This allow you to see real time the optimization. Okay. So this is just to define this neural network, right? From the neural network, and if you want to do the classifier, as we said earlier, is using these neural network classifier. Yeah, so it's just define this classifier, and you need to tell the classifier estimator QN. This is the from the neural network, the network, the optimizer, and if you want, also you input this callback function. Okay. Okay, so then we're ready to run this. So this set is empty set for list for this objective function value we're going to keep track. And you just say estimator.classifier. This is this estimator classifier dot fit. Right, X is the data, Y is the label. So we already print all these here. I think Y is actually yeah. Wait, Y is actually the coordinate on this dashed line. Wait, let's check. yeah, y is taking this y0, 1.
Under class, right?
But yeah, but it's y0, 1. Y0, 1 is this, and y is y this. Oh no, wait. Two times y0, this is 0, 1. And then if you do that, that just give plus and minus 1. We should get plus minus 1. Maybe my y was from other code, so other part of the code. So let me just run this again here. Yeah, that makes sense, right? Yeah, because I ran this at some point, right? And so that's from the later part, right? Yeah, that makes sense. It's a label, but it's using plus 1 and minus 1. It's not 0, 1. Okay. Okay, so maybe let me just let it run. Okay, so we have set up everything. Yeah, this, and we clear out our question why this, right? This is a label, so it's plus 1 and minus 1. Okay, so then you do this fit classifier fit, right? Estimator classifier fit. Right, and it has a callback function. So it would run that function and actually make the plot. So let me show you here. Right, this was the final, but if you run again, I run again. Oh, not showing. If you run it, you will see that it's actually doing that real time. But somehow it's just done on the computer here. Okay, you will see that it plot this real time. That is iteration. I hope you can see. Can you see maybe because I might have already, I need to maybe clean up the yeah. On this content, I think it's running, but yeah, it's running like this. That's cool to see the visual, visually that it gets right. Then you can predict. So this is predict estimator classifier that predict. You predict this, and it give you the predicted label. So let me plot this predicted label. So it's draw red circle for those which have the wrong prediction. If the target is not the same as YP is the label. It actually doesn't work that well, right? There's so many points that are far away from the boundary. I would expect maybe the stay probably appear here. And these are the ways you can bring down, you can compare with the initial one. The initial one we didn't save because it was already inputted randomly. Here. Okay. Yeah, so that was using estimator. Here we're going to use sampler. Sampler, you will draw distribution of 0 and 1. But the setup is very similar. So, okay, you have the quantum circuit, here we have only four variational parameter. Let's see if I what if I had repetition like 2? Let me see. I'm changing this real time to but okay, because the number of parameter above how many we have 8, right? And you only have 6 here, so maybe you're not comparing the same thing. So output shape, okay. And this is defined at parity. Okay, do the sampler. So this we define the sampler. It's still from the save vector. And you define sampler QNN, really similar to previously we have used estimator, right? We just changing the name from estimator to sampler. Everything else is similar circuit. There is interpret output shape 2 as the output number of output number results, and interpret using parity. Okay. Yeah, comparing to the estimator. The estimator is slightly simpler. Here we are using sampler QNN, and above we're using estimator QNN, which skips the circuit and estimator. Somehow there are 2 more input. And then the sampler classifier, this is from neural network classifier. This is the same thing except that you change the circuit sample QNN. And optimizer you can use this is classical optimizer, and let's go back. Okay, so let's run this. Yeah, running this is similar, right? You use sampler classifier that fit. Okay, and let's see if it runs real time. It's maybe running, but somehow it jumped. Yeah, okay, it's running, and it just finished. Okay, as a score, so they print out score. Yeah, I don't know. It's the score is not high, or 0.55, above 0.65. But this at least this can give you really small scale assimilations. This is the comparison. Somehow it worked very bad, especially for the points for a from the boundary. Okay, and this probably doesn't make sense to us, these numbers. And you can also use variational classifier. Okay, so we have these feature map using ZZ feature map, and ansatz repetition is 1. Maybe let me do a repetition 2, or even 3. Let me do 3. Okay, and you have to set up a variational quantum classifier. Okay, so you would say feature map is what you have defined, ansatz, right? And the loss function, what kind of loss function you're going to use, optimizer, callback, and what is your sampler? Okay, this is using sampler. Okay, this is using sampler we have already defined here. Okay, from this. And running this fitting, run the fit is the same. That VQC the fit, you give the X and the label. The label here is using one part, so it's giving a vector. Let me check or make comparison with previous. You need to be aware of what they want to use. Like classify you using Y01 simpler classifier. Yeah, estimator classifier using Y, which is +1 and -1, right? So you have to pay attention. I don't know whether there's option for you to make them uniform the same when you are running it in practice. Okay. It has a somehow higher score. Let's see the prediction. Oh, did I? Has not been fitted yet. Oh, I have not run this. Let's run this. I think it just finished. My screen keep coming back. Okay. The score is not as high as last time I ran. I think I ran that one was using only one repetition. Okay. Yeah. It doesn't seem to be performing very well. It's decent, but yeah. Okay, there is just multiple classes with VQC. It's here shown as like 3 set of data. So you have 0, 1, 2, or you can label it ABC. So I'm not going to run this. It's just another classifier example with 3 classes. The code essentially there's not much difference. So let me, in the interest of time, let me not do that. Okay. Especially example, just predict the label and the ground truth. They don't. I mean, it doesn't work perfect. I mean, it's for small, really small circuits, and yeah, only a few parameters. I think for classical neural network, you can use some decent number of weights, and you can make this classification very well. Okay. So let's move on to the regressor. So here the code block is actually doing a sine function, but adds some perturbation. So some perturbation, x is perturbed, y is also perturbed. It was uniform, but then you just make it not so uniform by adding x, a random number to the x part. And then there's some epsilon set to 0.2, the deviation from the original. Well, actually, it's not really, this is the factor times this ±1 number between random number between. And this is the generated, maybe we okay, generate this different instance. Then you do the regressor using estimator Q&A. So just really define the circuit, variation parameter, one. I think this is only 1 qubit. This is 1 qubit. We can plot this. Visual map draw. Maybe I need to decompose. Okay, it's really just a very simple. And then let's do the ansatz. Oh, this is Y X rotation and Y rotation. So very simple circuit. Okay, doing the regressor. You just say, I'm going to do the neural network regressor. And my neural network is this regressor. Wait, sorry. Yeah, here we define the circuit on the neural network circuit. And then you define this estimator QNN with a circuit estimator. And then when you want to do the regression, you define this class neural network regressor with a neural network being the one that you have set it here. It's a quantum neural network. So set it here and loss, what kind of loss you want. Optimizer, callback, okay. So basically, if you understand what the regressor is doing, then you know what need to input to this. Okay, and then you do the fit X, Y. So this is just one number. So X, Y, because you have one coordinate and the other is the function. So you fit X, Y. Okay, let's do the fitting. Oh, showing real time. And it's only 5 step. 5 step. If we do the when we set the optimizer, then we set, yeah, the maximum iteration is 5. The first step, second, yeah, converge seems to converge. 0.8, 0.98, that's a score is quite high. And you do this. It seems to work very well. Yeah. Let's see which one. The red is the target. Yeah, and the green is predicted. So that's not bad. Wonder whether this, yeah, this probably can also be used to, I'm not sure. What would be dealing with time sequence? 1 qubit. Okay. That there we use I think we use sampler. We use estimator. Sorry, we use estimator. You probably could also use sampler. But here, this plug is using the variational quantum regressor. So again, you have a feature map, ansatz, optimizer, OPEX, estimator. Okay. And then you fit. Okay, just 5 steps. So the score is very similar to others. Yeah. It seems to be some deviation. They're slightly larger than the estimator. Okay. So yeah, so that's the first notebook that I introduced. The second one I also uploaded. This one is training a quantum model on a real data set. So maybe I'm not going to do this in too much detail, but this is really from the data that's, for example, they use iris data. These are data you can download. Okay. And they are already built in machine learning, sklearn package that you can use. Right. So these are the data. Yeah, here it used the classical machine learning and then training the quantum machine learning. So it just showing you the circuit, the feature map. It has more, it has more. So this one has these four four numbers encoded here, but it encode again. Like here it yeah, here it encode again. This x0 and x1, x0, x2, x1, x2. So it's more complicated encoding of the feature. Yeah, this is the feature map. Then you also need to have the neural network part. That's the variational circuit. So use real amplitude. Yeah, this is 4 qubits, so this has more parameter here. Real amplitude. So this is called real amplitude. Okay. And then the optimizer, so very similar structure. And then for the quantum one, what I see here, they use a sampler and you also callback graph. It's so identical procedure, right? BQC, we have already seen that. Sampler, feature map, ansatz. That's all here. And you do the fitting, right? And then you test the score. Scores are not great. It's training. So here there's a training and the test data set. In the previous notebook, we always use this. We use the whole data to do the training, and we print the score that it predict on the training. It learned how it learned. So apparently didn't learn very well. Also here, somehow, yeah, it's only about 60%. So here, okay, reduce the number of features because we have 4. So here is reduced to 2. So reduce using PCA principal component list to reduce the dimension, and then let's see how it. Yeah. So also not so great, right? And then they change to a different answer, efficient SU2, and compare the score, 60 and 50. Yeah. So yeah, they have some comment here. And surprising, the classical model are better. Okay. They say, okay, classical machine learning has appeared for so many years, and quantum machine learning just developed recent year. But we reduced the number of features, the performance of all model went down as expected. Okay. So somehow it also depends on the answer, like using efficient SU2. I don't know how many parameters. May depends on the circuit, depends on the parameter, number of parameters, and yeah. So again, this is run on ideal simulator. So if you imagine running on a real device, maybe the result will be even worse. But this is for a really small circuit, and you can increase that dimension. So the next one that I'm going to discuss is this quantum kernel. Okay. So what they say here is for many data set, the data points are in a higher dimension. And then what you want to do, maybe you just want to compare the distance in some sense of different points, and then you want to do the classification. Okay. Okay, list the reference. You can take a look. Okay. So kernel basically is some kind of distance um, or similarity or yeah, in here like overlap. You can define this as overlap. So k is the kernel function. So you can imagine that there are measuring some distance. The f map to n dimension to m, so you can reduce the space. A denote the yeah. So this is the inner product. So in order to do the kernel method, you need to measure that using quantum circuit. So you have to measure the overlap. Okay. Okay, maybe I should run this. Yeah, so here we are going to see the classification using from the kernel method. Okay, data sets. So there's some ad hoc data, so loaded there. Let's not worry about the detail. Basically, load data. Okay, this for example, training size, test size, dimensions two, gap. The gap I think is if you have different cluster, how close they are or how far apart they are, characterized by the gap. Okay. They define some function plot feature map plot data set. Okay, so plot it here and we'll show the data here. Okay, so this is a visualization of the data set. So the blue is in one class, the red is in the other class, and this is square is training data for class A, circle red, empty circle red is taken from the other class, and then also a few points for testing. Okay, to define the kernel map, we use the oh, I accidentally clicked that. Okay, but it's this fidelity quantum kernel class. Go back. And has two arguments. Feature map. So we're going to using ZZ feature map. Fidelity is the way it's called compute and compute fidelity. Okay, you can. So basically, it compute this class leverages the sampler primitive to calculate fidelity of two quantum circuit using this compute and compute method. So This is defined this paper. Supervised learning with quantum enhanced feature map. This is in this Nature paper. Okay. So these are the standard package primitive for state vector fidelity using this compute on compute. So you get an overlap square. And for machine learning, import fidelity quantum curve. Right. So define the feature map dimension, it's ad hoc dimension. You have repetition 2, entanglement structure, linear. We define sampler and fidelities, how we compute using this function, compute on compute. And the kernel would then be this fidelity quantum kernel using the fidelity definition way to compute fidelity feature map. Okay. So far, there's nothing variational here because we're just measuring the overlap. Okay. Classification, also using support vector machine. Yeah, this define kernel. Okay. Providing the kernel as a callable function, recomputing the kernel matrix. So we need to compute this overlap. This overlap here. Here. Okay, so you want to do the support vector. Support vector. What is support vector classifier? I guess classifier SVC. Okay, so you need to define this, and the kernel is this ad hoc kernel that evaluate. Ad hoc kernel is this computing the fidelity, right? Define the class, and then when you say evaluate, then that give you evaluating this, and then you do the fit. You do the fit with train feature and then train label, the score. Oh, okay, this is the score. And yeah, train this. Okay. I don't see the callable anywhere mentioned here. Okay. It's running, so it's running that, evaluating the kernel and then using that to do the fitting. Okay. Callable kernel classification test score is 1.0. Okay. Recomputed kernel. Okay, so extract these train and test matrices. Evaluate. So we say kernel evaluate X vector equals train feature. And test. You say X vector equal to test and then Y. So for yeah, for this, you just need to evaluate with the train feature. So you get the matrix. And here to test, you need to know. Wait, why is this the train feature? Oh, so I think it's comparing the test feature and with the previous. So you have new data, so it's really just looking the overlap. Okay, so let's plot this. Where's the Okay, and then this ad hoc training kernel. So this is really between the kernel itself. So there are zero, I think there are around 40 data points. Actually, okay, 20. I don't know why it's labeling that like up to 40. Two points. I think they are 80. But this is the overlap, right? So diagonal will always be one. And this is measuring the overlap. And this one is measuring the overlap of the train and the test. Test there are, looks like there are 10. Data set. Probably we could probably just see how much the data is. 9 or LEN. Train feature. Forty and 10. Okay. Somehow I saw 20. Where was the 20? But okay. Anyway, we from the diagram it's obvious 40 train feature and then 10 test feature. Okay, so now we to use these matrices, we set the kernel to a new SVC to pre-compute it. Okay. And then you fit this ad hoc matrix train labels. Okay, and then you give the scores. This fit here is essential. And you use the pre-computed with ad hoc matrix train and train label. This is where the ad hoc matrix train is. Here. This is for the total. This is for total 50 data point. And so yeah, so they separate into the two parts, training and testing. So recursive kernel classification test score 100 seems to be very good. Classification was wonderful. So this here so far, let's see. So far, looks like we are doing the classical. Because there's no quantum part yet. So it's only at this part is the alternative training algorithm. Take the quantum kernel instead of the kernel evaluation of above. Yeah, so this is, but it said the quantum kernel can be plugged in. Where is quantum? Is there a quantum? Any place that's quantum? Ad hoc.
Kernel is
Oh yeah, here there's already kernel evaluating using the math feature. Yeah, so there is a quantum here is to evaluate ad hoc kernel. Okay, so the only quantum part is really just evaluating that overlap matrix. It could also be done by classic. So this QSVC is an alternative training algorithm. Okay, it says it extension of SVC that takes a quantum kernel instead of kernel evaluate. Okay. So the only difference is quantum kernel equal to ad hoc kernel. Here, it's using ad hoc kernel that evaluate. So the only difference is here, or the major difference is there. Here we're using evaluate, ad hoc kernel that evaluate. And evaluate will be evaluating this fidelity. Here it's using F. So let's run this. So again, this is like packaging in a way that it's now it's a car. You don't know exactly what's inside, what's the engine, what's like, but at least uh you could use it to train. If you really do not know anything about quantum, but you just treat it as another machine learning method, right? So it's a black box for a machine learning user. Okay, the score is perfect, 1.0. The average score. This really looks very good. Okay, so clustering. Okay, that's another data set. This is using a larger gap, so there is a parameter gap somewhere. Yeah, here. So 0.6. Previously was I think 0.3. This is a different set. Yeah, 0.3 here. And defining the quantum kernel. Okay, this is similar to a previous. And spectral clustering model. Okay, but this is doing exactly the same thing as previous, right? Ad hoc matrix. Then you use that to do the clustering. They will introduce training and testing. Okay, this they here somehow their classification they don't. It would be nice they we could plot and visualize what is exact output. But if it says 1.0 the score, then they get really good classification. Okay. So the final one is to compare with this kernel PCA Gaussian and quantum kernel. Gaussian, yes, it's possible. Or is that to a Gaussian kernel and pre-computed more important? Okay, maybe I did it wrong. Did I? Let's, yeah. Something wrong. Oh, the array with zero sample. So maybe I didn't generate the sample. Oh, I did. Okay. Run. So this is to compare with the classical one with the Gaussian kernel. So Gaussian kernel would take roughly would take point here, point there, and compute the distance and then put in the Gaussian function. That's what I imagine that it could do. Okay, here we try to score. Okay, logistic regression score 0.95. Let's plot the result. Okay, finally. Okay, projection of the training data and test data using K PCA kernel PCA with quantum kernel. Projection of using kernel PCA. So there is some errors here, but this is close in the middle, so it's good. This one. Yeah, I wonder why these two are different in the sense that not the same data showing up on this principal.
What's in different kernels, right?
They're using different kernel. One is quantum, one is,
Yeah.
but the location of the point, or maybe because they get transformed.
This is kind of like, it's kind of trying to show that the quantum kernel is somewhat better than the Gaussian one,
Yeah,
because it's no longer, but for the Gaussian one are separated,
it's what
right? Because the Gaussian one doesn't make the, you know, make it linear separate. But the quantum one does.
Hmm. Okay, so maybe there, yeah, there's some explanation here. The data points on the right figure are not separable, but they are on the left figure, as you said, because somehow, yeah, so they were plotting this not in the original data.
Good.
They're plotting in the transformed.
Yeah.
So on the left, you see that using quantum somehow is so easy, you just cut. But for the classical, Gaussian, then there's no way you can cut clearly. So yeah, for the in the sense of quantum kernel, you transform these points so that it becomes easier to separate. Okay, and this is why simple vector machine classifier works perfectly well on the ad hoc data set result classification. Okay. Yeah, so maybe I won't go into the Qiskit nature, but we cover 3 notebook. Not in as much detail in the past, but in some depth, I would say. This will be the electronic structure next time, maybe. I will briefly mention, I think I have 3 notebook, but will be much less detail than this class. Because I really want to get started on our next